I'm pretty excited to be here. This is a system I think I've been working on. I don't really want to count, but it's probably been for about a decade now. So I'm just going to kind of give a brief introduction to what we've been calling the Strongback system. And before I really wanted to get started, I just wanted to point out that the Strongback is actually part of a family of these spine systems that really they employ an essentially elastic vertical steel truss or mast, either embedded or away from the primary seismic force resisting system. And so concrete shear walls, uplifting rocking brace frames, and then this figure on the right, which is what I've been calling sort of the Strongback brace frame, and that term was kind of coined by my advisor, Dr. Stephen Mahin, all sort of employ this idea of a spine. And from that perspective, many of these systems kind of have these similar behavioral characteristics. So I'm going to focus on the one on the right, but just so everybody keeps in mind that it's really a family of these spine-like systems, and a number of researchers have looked at other variations of this concept. So when I initially was putting together this presentation, I thought it would be easiest just to go through the many projects that have been funded so far, sort of looking at this Strongback spine concept. And there's been a number of collaborators on the way, and I by no means want to focus just on the work that I've contributed to the system. And I'm just going to kind of put it in the broader context of the earthquake engineering community. So in 2013, there was actually a grant that was looking at the behavior of older or vintage brace frames. And that sort of stemmed into the idea of this Strongback or spine concept. And so what we were seeing, and what has been documented after a number of previous seismic events, is that brace frames tend to concentrate damage in a few or single stories. And so you can see this figure on the left, you're getting almost all of the demands and damage concentrated one story. You're not mobilizing the full energy dissipation of the entire system. Really, you just have the entire roof drift then only concentrated in a single story. And so the idea of a Strongback is to design a portion of the system to remain essentially elastic. And by doing that, you provide an explicit elastic load path where you can distribute the demands across multiple stories. So how I like to typically describe it is that, in a conventional system where you have concentrations of demand in a single story, it's really 100% of the damage in one story. And you get a sort of averaging effect when you start employing the Strongback, where you have, and say this is a 6-story building, you now have a sixth of the damage distributed across all stories. And so the concept is that in general, your peak story drift would be reduced and structural damage would be reduced as well. And so this is just another figure that I often use, but in sort of employing one of these Strongback spines, you can vertically propagate demands. And because of that, you get to have increased design flexibility. So you can avoid sort of mass irregularities, stiffness irregularities, by spanning across those stories with the Strongback system. If a brace were to fail, let's say either by fracture or some sort of rupture of the steel core of a buckling restrained brace, then you can still span across that story, provided you have a Strongback that's stiff and strong enough to remain elastic when that occurs. So it really does give the engineer more design flexibility. And it's really also the product of a number of different previous researchers. So a number of studies have sought to look at different methods of mitigating this story mechanism behavior. And I'm just showing the zipper frame on the left, but there's also been dual systems where you have a backup moment resisting frame used in conjunction with another seismic force resisting system, using the columns to sort of provide that elastic load path. I already kind of mentioned the shear wall concept, rocking and self-centering systems, and again, just the zipper frame on the left. And so the Strongback is another variation of that theme, except that it's really the design of a very stiff and strong elastic steel truss that's embedded. Typically, it's shown within the same bay as your brace frame system, but it could also be in an adjacent bay, or even separate out entirely. And so what it does by having sort of an elastic portion of your system that's designed to remain elastic, when you start looking at the kinematic mechanism or the plastic mechanism of having that elastic portion, you sort of get this pivoting type response, where you have, a portion of this triangular portion of the system, which is designed to remain elastic, that pivots back and forth about a pinned, or we've also looked at sort of a weak axis column base. And in the case of this was one of the first experiments that I did on the system. It was a 2-story brace frame with a buckling restrained brace as the primary energy dissipating mechanism. And then it used the beam and it had flexural yielding as sort of a secondary energy dissipation mechanism. Now notice that because of the kinematics of the system and this sort of pivoting motion, you're actually getting pretty large strain demands, axial strain demands on the BRB, and you're also getting pretty large rotational demands that you'll see on the beam. And so one of the things that you sort of have to consider is the geometry of that mechanism, of that pivoting back and forth, and make sure that that's adequately designed for and detailed. And so this was the experimental test that I conducted during my PhD, and here you can see just this Strongback portion of the system that was designed to remain elastic. And this was the experiment, and we pretty much got that behavior, that pivoting back and forth behavior. Now the issue with this experiment is that it really didn't look at the dynamic response, and I'll have a couple slides just kind of on how the dynamic response is very different than what you're seeing in this experiment, as well as that sort of that figure of the plastic mechanism. So this idea kind of started catching on, and so it was funded by AISC back in 2017, and it'll be funded again by AISC starting next year in 2022 to sort of look at the system and how it can be incorporated into AISC's seismic design guidelines. And the idea initially when it was funded in 2017 was that there were a number of numerical studies, there was this experimental tests, as well as some work done by others, and it was started to be implemented sort of as this very stiff and strong elastic truss in practice, but there wasn't really an idea of what this nonlinear dynamic response of these systems might look like and how you would adequately proportion this truss, this Strongback truss, to remain elastic. And so this project sought to understand that a little bit better, and what you end up seeing is that when you subject systems employing spines or very stiff vertically elastic elements to seismic demands, much like a concrete shear wall that you see here, you see kind of an interesting phenomena. So in the case of the concrete shear wall, which again behaves very similar to the Strongback system, here you have sort of a first mode response where the force resultant of whatever those inertial loads are is maybe at this height h hat. You're forming some sort of plastic hinge at the base. I'm just calling that M1 star. And then just by equilibrium, if you take about the base, you can say that the base shear by some sort of capacity design is just going to be that moment divided by h hat. Well, the issue is that's just accounting for the first mode of response. And so as you account for higher modes, then that force resultant wants to shift down. And what you start seeing is that you're still constrained by the yielding at the base of the wall. So that's still M1 star in this case. But because now you're dividing by a smaller height, or a smaller height of that force resultant, you can actually see larger base shears than you would just by the yield mechanism under the first mode. And so I've been calling this the near elastic higher mode effect, and it can result in base shears, story shears, acceleration demands in the higher modes that are not necessarily limited by the yield mechanism of your system. And again, that's in the higher modes, not the first mode. And so that sort of results in some sort of tricky design requirements in order to account for these higher mode force demands. And even worse, when you start looking at the higher modes, it's very ground motion dependent. So now you're looking at what I'm calling near elastic higher modes. So they are near the elastic response spectrum. And so it is highly ground motion dependent. And so it's not like you're constrained by yielding in the system. Now you're actually dealing with elastic or near elastic response. And so it's extremely ground motion dependent. And so if you have ground motions that have higher mode frequency content, then it's going to result in larger forces. And if you have ground motions with lower frequency content near your higher modes, it won't necessarily show this higher mode effect. But it is important, and it's something that we need to design for in order for that Strongback to remain strong enough and be a reliable system. And there's a number of different ways that people have sought to sort of characterize this effect. I've sort of looked at employing a modal pushover analysis, and I think the paper that I wrote on that has been sent out. I can talk about that more if anybody's interested, but it basically combines the response in multiple modes. I should say not exactly theoretically accurate, so I can also talk about that a little bit further as well. There's also been a number of researchers who have sort of proposed this modified response spectrum analysis, where you use a truncated response spectrum, which represents an elastic response spectrum in the higher modes, but then you reduce by your 2/3 to get the design earthquake, and you reduce by R to account for sort of inelastic response in that first mode. So there's a number of different ways that can be used to sort of look at this. So you could think of it as using an R equals 8 for a BRBF system, an R equals 8 in the first mode, and maybe an R equals 1 in the higher modes. And so that idea, and this will be the last few slides that I have here, sort of led to this most recent research activity, which was how do you address these higher mode force demands and the acceleration demands. And so this was a project where we looked at, there's a number of different ways that researchers have sought to mitigate these higher mode force demands, but this is just the one that I happen to be involved with right now, where we're employing what we're calling force limiting connections. And so they're connections that yield, and they're sandwiched between whatever your spine is and whatever your base frame system is. And it gives you some controlled yielding so that you can control those higher modes and that they're not basically in the elastic range of the response spectrum. And so here is one of the force limiting connections, or FLCs, that we looked at, which was this U damper, and then we also looked at like a T-shaped damper. And the characteristics of these dampers are fairly specific. They have pretty high post-yield plateaus, so high stiffness after yielding. And there was a number of design considerations that we're still trying to figure out for these force limiting connections. And we actually tested this at eDefense, which is, right now the largest shake table in the world. And you can see the U dampers here. And in this case, we're not using a truss as a spine. We're actually using a very deep column. And that's just because we don't really have a lot of mass associated with the system. It's only a 4-story frame. It is at full scale. But it's not exact. It was fairly small compared to some of a realistic building, for example. And then we tested it under a number of different ground motions and sort of looked at those ground motion characteristics. And when those force limiting connections weren't engaged and we kind of locked them, we actually saw quite a bit of non-structural damage due to hospital equipment. So in this case, we were really looking at sort of hospital type buildings and the equipment associated with that. And you can see here, so this top series of videos is just the frame and the spine. And then this second series of videos is the frame, the spine, and then the force limiting connections. And you can really see the difference in the accelerations. So again, look at the top series of videos, and you're going to see that you get quite a bit more motion, and that's due to those near elastic higher mode effects. This is again under the same ground motion, but I just want to be clear that this is very ground motion specific. You have to have a ground motion that has content near your higher modes to get these sort of effects. And there's a number of other methods that you can sort of mitigate these higher modes as you design these Strongback systems. And then there's been a lot more recent work that I've been involved with extending this concept to other materials, mainly mass timber, and I could talk about that more if anyone's interested in that as well. For me, it's really the design flexibility, and I mean, I think Leo really hit it on the head, is that when you're looking at drift, you can really control it by employing this elastic element. It's basically a mega column in your system, and it gives you a lot of different variations on that general theme. And that's just very exciting. I mean, there's lots of things like theoretically I'm excited about, but I don't know how much everyone on the call wants to hear about that. Like, so for me, the higher mode effects is also quite interesting just because it's so much different than a traditional seismic force resisting system. But in terms of design, it's really that design flexibility. Like it's kind of unmatched in that respect. So there's been a number of studies on this. And from my perspective, we've gotten a lot better at brace frames. We have compactness requirements for, in the case of an SCBF for the braces. Leo mentioned the fold lines. We have, sort of the like strong beam requirement, which we can talk about whether that might be inducing more story mechanisms or not. So we've definitely improved, but there is a tendency for the system to form story mechanisms, and that's because when one of the braces in a story either yields in the case of BRBF or buckles in the case of a concentrically braced frame, you're going to get a loss of stiffness associated with that. And so with the loss of stiffness, drifts are going to want to concentrate in that story where inelastic behavior was initialized. And unless you have some pretty stiff columns that are able to provide a load path and distribute demands to the adjacent stories, you're going to continue to concentrate damage there. The drifts are just going to want to continue to go to that location. And so that's something we see a lot in numerical analyses, but we've also seen it in a number of experimental tests. You have to be kind of careful with experimental tests because there are ways of inducing these story mechanisms in those experiments that might not be realistic. But there's also been a number of that type of behavior, that story mechanism behavior documented after past earthquakes. And my favorite one is after the 1994 Northridge earthquake. There's a number of papers about that building as well. And you go and look at where the documented damage is, and it's all in one story. Like there's, going through the building, like none of the other stories had any damage. So it's something that we see. I have to say it occurs to a lesser extent in BRBFs, but that tendency is still there. I should also say it depends on the severity of your ground shaking. It's a good question, and if I understood my past advisor's mind a little bit better, maybe I could tell you the answer. He had a number of ideas, and it was always a different idea with him. But when in the 80s, he was working with a student on the zipper frame. And what the zipper, and it looks a lot like the Strongback system, but what the zipper frame in concept is you would put in a vertical element within the brace bay. And then you would allow the braces to buckle and yield, and that would create an unbalanced load that would then pull down or push up on that strut. And by pulling down and pushing up on that strut, you would engage adjacent stories. And so that was sort of like a way of preventing story mechanisms. Around that same time, you were seeing a lot of work being done on dual systems. And you had to be kind of careful about considering how the load was being shared across these different portions of the system. And those are in the code as well. So zipper frames are in the AISC commentary, and dual systems are of course in AISC 7. And then you're seeing a lot more prevalence of these other sort of types of I'm going to call them spine systems in terms of the concrete shear wall, and then the rocking or uplifting systems that conceptually have a lot of similarities. The one difference is when you look at the Strongback system, at least how it was originally sort of thought about, it looked like a brace frame still. And so there was a practical component that I think people kind of gravitated to, that it still looked like a brace frame. There wasn't anything sort of really strange or out there with it. It wasn't uplifting. It was just, you're going to design a portion of that system to remain in the elastic range. I've seen a number of rocking systems that have been constructed and designed and built, and they've also been experimentally tested. But I think the Strongback portion, again, how it was originally thought of, is very practical in that it looks familiar. In an ideal situation, you would run a number of nonlinear dynamic analyses, and you would look at the forces that develop in the Strongback portion of the system, and you would design them with a larger capacity than those forces, and then include some, a couple other factors to account for any uncertainties that you're not embedding into the numerical model. When you start looking at sort of simplified approaches, then you have to kind of look at it at a larger scale and really do something like what LRFD does, where you embed the uncertainty into the problem. And so much like in LRFD, that you have a demand and a probability distribution associated with it, and you have some sort of capacity and a probability distribution for it, you want to sort of minimize that portion where you get failure, or in this case, some sort of inelastic response in the Strongback system. Now that's if that inelastic response is not controlled. And so there have been a number of researchers that have sort of controlled yielding in the Strongback portion of the system to sort of mitigate higher mode effects. And that's different because those are detailed to be ductile, and they're detailed so that you still get, a pretty uniform distribution of energy dissipation over the height of the system. But that's, I think, different than the classical Strongback that I've been showing, where you design to remain elastic and it's ordinary details. And you just have to ensure that it's strong enough, much like you would ensure that a column is strong enough for those probabilities. So you kind of reduce that risk as much as possible. There is inherent redundancy that's coming from other things, like the gravity framing, for example. So it's not like the Strongback is going to fail and then the entire system collapses. There's other redundancy that we often don't take into account in design, but when we do like a collapse analysis, we would incorporate those other methods of load path. Something rather than the focusing on the redundancy factor too much, I mean, there are other benefits of sort of employing a Strongback that you could alleviate certain design requirements other than sort of like the system level design requirements. So for example, the use of ordinary detailing in the Strongback. Potentially you have smaller strain levels in your buckling restrained braces. If you have smaller strains, your omega and beta factors are smaller. So you're dealing with perhaps like smaller adjustment factors when you do capacity design for the BRBs. So there's things that come into play. If you use it in a moment frame, for example, then strong column, weak beam requirements could be sort of alleviated because now you have this one like mega, I'm using the word one, but a one or a few mega strong columns. And so there's other sort of design scenarios that you could come up with where you could alleviate some of these sort of standard requirements and make the system more accessible. I don't want to say that that's what you're aiming for, but you're trying to like get the energy dissipators to dissipate energy. And then the Strongback, you want to make sure that reliably is designed so that it remains in the elastic range, or at least is controlled if there is inelastic behavior. You as the designer sort of determine that level of detail. So if you decide that the Strongback needn't remain elastic at some intensity level, then detail it so that if something does happen, it's capacity design and you spread that load elsewhere, and you don't affect like the load carrying capacity of your system. So I think that's really the responsibility of the designer. And if you want it to remain elastic, design it to something above the MCE level, where it's a very, very rare earthquake. And I guess I just would like to add that little conservative researcher in me, I mean, doing a complete FEMA P695 collapse assessment where it's peer reviewed and you have all the uncertainties checked is needed before anything is going to ever make it into the code on a system like this. And, I see that there's a couple people on the call that have been involved with my meetings in AISC, and we've sort of discussed maybe piggybacking on an existing system, but that still requires that collapse assessment. And then when you start looking at adding any sort of new system into AISC 7, that's problematic in of itself. So at least for me, what I've seen is, I mean, you know, you can read the papers and you can like go through all the research, but it's really not in the codes right now. And given this sort of odd behavior with the acceleration, the higher mode acceleration and forces that are, you know, I would say different than a conventional system, and need to be accounted for. Like there are some special requirements, and I just don't think that there's been a lot of linkages with that yet when it comes to like what's actually in the code. You're starting to see it in ACI. I don't know what everybody thinks of it, but I've heard a couple of rumors that maybe it's a little bit hefty in ACI, where they're accounting for these higher mode force demands. But for me, it's like there's a couple questions that are still out there, and those are needed before it's going to be more widely adopted.